In this last video on section 5.1, I'm hoping to wrap up and review what you've seen in the previous two videos. Also, the idea of having significantly high and low values gets revisited. So this is how it all began 2 videos ago, is what does it even mean to have a probability distribution? And as I mentioned in that video, there are 3 conditions. In a sense, in my mind, it's like 2 conditions. So I won't ask you to write exactly what you saw in that video, but recognize when you have a probability distribution and when you don't. So this is a different question, a different context. A hospital researcher is interested in the number of times the average post-op patient will ring the nurse. For those of you guys that are in the nursing program, right? Or have been in the hospital, this is relevant to you. There's a random sample of 50 patients, and X in this example represents the number of times that a patient rings a nurse during a 12-hour shift. So this is the 50 part of this, of the setup of the problem, is that's the total. And then the maximum, apparently, that any one single patient rang the nurse in a 12-hour period is represented here. So there, you had 4 patients that didn't ring the nurse at all, 8 patients that rang the nurse once. So why are you studying this? Partially so that if you see an issue, you have some measure of statistics that you could apply to present that issue to help with staffing needs. The side of it is, from outside of this class, I might ask you to read a context, take a set of data, and create a probability distribution out of it. So yes, know that slide. What are the 3 conditions to check to see if you're being presented with a probability distribution table? But also think about, how could this be useful maybe to you? How do you become this data analyst in the field that you're in? So the question down here at the bottom is, why is this a discrete probability distribution function? It says 2 reasons. First reason, the first column, what we're counting is the number of times, and that could be expressed with a number, and it could be expressed with a discrete number. The second reason, even though there are 3 conditions, is that these represent the probability of each of the possible outcomes. And the third condition on the other slide was that these all add up to 1. Well, I don't remember if it was the second or the third. Again, so I'm meshing your textbook a little bit with other sources, but yes, this is a probability distribution table for those 2 reasons. So like I said, I want you to be able to create your own probability distribution. I'm asking you to take notes this week for this section, instead of infusing the quiz questions. And so try to do this independently, like on your own. Maybe pause the video and then maybe watch me do it. But this is a quick check to see how you're doing with this section. Jeremiah has basketball practice 2 days a week. 90% of the time he attends both practices. 8% of the time he attends one, and 2% of the time he doesn't attend either. What is X, and what values does it take on? Let's create a probability distribution for Jeremiah. And if you want to pause before I jump right in, it might be a good idea. Here we go. So Jeremiah could either go to practice twice, nonce is not a word, no times, once, or twice. And so that is what X represents. X represents the number of times Jeremiah attends practice. Per week, right? And so the first column in our table are all the possible times. Well, if practice is only held twice, the total possibilities would be no time, 1 time, or both times. And then you've got this 90% of the time that he goes 2 times a week. And so that would be for the 2. That's the probability we present there. For both practices, 8, only 1 practice. Remember, 8 is 0, 8, not 80. That would be 80. And then 2% of the time he does not attend either. And so the mean of this is what you saw in the last video. To calculate the mean or the expected value, what you're doing is basically like a weighted average that you saw in chapter 3, that you would do 0 times the 0.02, add that to 1 times the 0.08, and then add that to 2 times the 0.90. And so what you're coming up with is a likelihood of how many times per week he would probably show up to practice. I did it, so might as well work it out. So this would be 0.08, and then this would be like a math teacher, 1.80. I'm going to double check that stuff for you right now, that just so that I don't go too fast, right? 2 times 0.90. And that is 1.8. And then you add this, so 1.88 times is the expected number of times that you can expect that Jeremiah will go to practice out of 2. Again, sometimes this expected value doesn't come out as a discrete number, and you take that, you know, as a consumer of knowledge when they say, you know, the average number of kids per family is 2.7, you know that that's impossible. So you round up or down, but, you know, being in a stats class, you're smart and you can interpret that kind of information. So what this is going to start leading into in the next section is something called a binomial distribution. These are not all binomial distributions because they're not symmetric. And what they are just probabilities of different events occurring when the possible outcomes are countable. So another example that you could just test yourself, or I just want to talk through, a baker has decided how many batches of muffins to make to sell in his bakery, and he wants to sell enough to sell every muffin and no fewer. And through observation, this mathematical baker has made a probability distribution. You don't know how many days he is looking at or he's considering, but what you can tell is if he makes either 1, 2, 3, or 4 muffins, what the percentage of days where he sold all 4, or where he sold 3 out of 4, where he sold 2 out of 4, and where he sold just 1 muffin. So again, I would pause the video. From your perspective as a student, you don't see a ton of examples. You know, you're having to watch this 10-minute video, 15-minute video, jump into Pearson and try to answer these questions. And I just thought the material's getting a little more challenging and I should provide more examples. So please try to read through the questions, answer them on paper. I am asking you to turn in your notes for this section because it is getting a little more challenging. First question, what is the random variable X? Second question, what's the probability he will sell exactly 1 batch? So my fault. It's not 1 muffin. He wouldn't be able to make a business. What's the probability that he'll sell more than 1 batch? And on average, how many should he make? Okay, so that first question, the random variable is the number of batches of muffins per day. Yep. Okay. Question B. The probability that he will sell exactly 1 batch is 15% or 0.15. And now we're going into how these questions should get more challenging. What's the probability that he will sell more than 1? Well, more than 1 is not equal to 1. So that would be either 2, 3, or 4, and you would add all those together. So that would be 85% chance that he will sell more than 1. And then finally, the on average, how many batches should he make? That would be if you were to calculate the mean or the expected value. And you see me grabbing my calculator, and what I'm going to do is go into L1 and type in 1, 2, 3, 4 in list 1, and then I will type in 0.15. This is something that you want to get good at doing in your own calculator. I also have a video where it'll show you how to do this, what I'm doing in StatCrunch. But you can't bring StatCrunch with you when you come to take your exams. So again, what I just did and what I hope that you do is go into your calculator, enter this data. And so I've got all the number of batches, and then I have the percentage of times, or the probability that he sold how many out of 4 batches. I'm going to go to Stat. I'm going to go to Calc, and you are calculating one variable, statistics. But now we've got what's called a frequency list in L2. And so he should make about 3 batches if he's wanting to sell all of them. And he doesn't want any to go to waste. This is the expected value with the standard deviation of 0.865 of a batch. So the last little bit of practice in this section 5.1 does go back to something that you were just studying in chapter 3, and it's the concept of having a significantly high or low value in a set of values. And so that high or low value is going to be one of your X's. You saw me kind of flip through these slides. I will have the slides outside of the video for you to go back and forth with. I don't like my videos to go too much longer than 10 minutes. And so this is just something for you to consider, nothing that I'm going to do anything with right now. So let's get to this last bit, the idea of having significantly high results, dealing with probability. So this text at this early stage, we're in chapter 5, hoping to get through chapter 10 and a little bit of 10. So you're doing good, you're doing well, and we're headed towards the real meat of this course. The meat of it has to do with what do we consider significant, and so we can make a claim or statement about our results, like we think they're significant and we want to say something about it. So in dealing with probability, 0.05 is a low likelihood. And so what you see here is the idea that we can call an X value significantly high if anything more than that X value has a probability of less than 5% happening. For example, the baker, if he made 20 batches and the probability that he would sell 17 or more was less than 5%, then him ever selling 17 is pretty significant, right? So it's this idea that if you sell more than that, and we've got data that less than 5% or 5% of the time you don't sell more than that, then that number that you sell is significant. And so there's a little contrast, a little something for you to think about, that even though it's a small probability, we're calling that X value high, because anything greater than that is not likely to happen. It's got a low probability. But it does go back, and the other end of the tail is also true. You have a significantly low value of X if anything that and less occurring has a probability of less than 5%. On the previous slide, they said this 5% or this 0.05 probability is not rigid. It really depends on the situation, and that's how this class gets just that harder. Later in chapter 7 and 8 is dealing with these different decimals that are small, and then having to translate that into what does that mean when I get 0.0001. Is that like good or is that bad? At this point, it's a low probability, and we call that significant. So you still have this range rule of thumb where you got the mean and then you subtract 2 standard deviations. But as I mentioned in some videos, you're not going to have to calculate the standard deviation on a lot of these problems. They will give you that information, and you need to know the range rule of thumb is that I take the mean, I subtract 2 standard deviations, and I take the mean and I add 2 standard deviations, and this is actually giving me boundaries. Anything to the left of that is significant. Anything to the right of that is significant. So I'm hitting the 15-minute mark, you guys, but I hope that so far it's made some sense. Hi, baby. And let me do this one more example, and I hope it helps. So we found that for 2 births, again, coming back to this, having number of babies in a family or number of children in a family, and we did actually find the expected value of 1 girl if you had 2 children, right? You could have, we did it. Okay. And so the standard deviation, we didn't do that by hand, but it's being presented to us. That's a probability distribution that we did a couple videos ago. And so the question is 2 female at a 2 birth significantly high? And so to do that, I'm grabbing my calculator, and what I'm pressing is 1 plus 2 times 0.7. And that calculation is supposed to tell me the value of the number of girls that is considered significantly high. You see the answer already as I'm fumbling. So 1 was the expected value. 2 is because significant values by the range rule of thumb is 2 standard deviations. And then 2.4 is considered significantly high. Again, it's very challenging trying to make sense of something that doesn't make sense. How are you going to have 2.4 girls if you only had 2 children? But what you are doing are the principles of what's considered significantly high or low. And so because 2.4 is not greater than 2, we don't consider having 2 girls when you have 2 children to be very significant. It happens. Now, add the number of children. Like my mom had 7 children, and 6 out of 7 were girls. Like, it happens. But 7 out of 7, whew, when you have 7 children, for all of them to be girls, that would probably be significant if we were to create the probability table. I am at 17 minutes, you guys. I am so sorry. I'm hoping that these videos become a little bit more bite-sized, but I don't want to under-explain these concepts. If you have questions, remember our Q&A board. Good luck.